Yes, I'll talk about resolution analysis. And okay, so first of all, I gratefully acknowledge the support by OpenSF. And so analysis of resolution of tomographic reconstruction from discrete data is practically quite important. The usual way to solve it is in the setting of the sampling theory applied to the classical Radon transform. RT here stands for the Radon transform that integrates over hyperplanes. And the key assumption in this approach in sampling theory is that F is essentially band limited. A number of very nice papers have been written on the subject by Frank Natterer, Adolf Eridani, Laurent Debar, and others. A recent extension of this theory by Plan and Stefanov allows consideration of more general Radon transforms and allows F to have at most semi-classical singularities. Typical questions addressed by the sampling theory are like these two. Given an essential frequency bound of F, how fine should the data RF be sampled for an accurate enough recovery? Or given a fixed sampling rate of RF, what are the smallest details of F that one can recover? Okay, so frequently one would like to know how accurately and with what resolution the classical singularities of F, for example, a jump discontinuity across a smooth surface, are reconstructed. So our question here is different from that is studied by the sampling theory. The question, it's here in blue, what does the reconstructed image look like near S, the singular support of F? So as you can see, it's different from the first two. It's related, but it's different. Okay, so the rest of the talk will be about this question. What does the reconstructed image look like near S? Okay, to illustrate the ideas, consider a simple example, exact inversion of the classical Radon transform in R3. We assume that F is particularly simple, it's piecewise constant, it equals 1 inside a domain bounded by the smooth surface S and equals 0 outside. Okay, so we pick a point x naught on the boundary and normal vector C naught, and so the C naught here is in green, and plot the values of F along this green line segment. And we'll get the value 1 inside in the interior and the value 0 in the exterior. Okay, so this is our exact reconstruction. This is what we would get if we had exact continuous data. So suppose now we have discrete data, right? We take discrete data, we interpolate it somehow and stick it into the exact inversion formula. We'll get some reconstruction F epsilon. F epsilon. The question is, what does F epsilon look like? So, so instead of this step function, the ideal response curve, we'll get something that looks like this blue curve. So this is the question that so our goal is to figure out what this blue curve is like. Okay, so let's discuss this approach more specifically. Right, so so what I'm talking about does not apply only to exact reconstruction, doesn't apply only to functions that have jump discontinuities. So it applies to fairly general reconstructions. For instance, lambda tomography is reconstruction that enhances edges. Right? So it's edge enhancing reconstruction. So the approach here applies to all of these reconstructions as well. Okay, so let's talk about the main idea. So S here is the single support of a function. Right? So we pick a generic point x naught on S, and we consider an epsilon size neighborhood of the point x naught. Then we dilate this neighborhood by a factor 1 over epsilon, such that it becomes, in terms of the dilated variable, check x, it becomes a finite size neighborhood. Okay, we fix the dilated variable check x, multiply the reconstruction by epsilon to the power kappa, and take the limit as epsilon goes to 0. It turns out that for one specific value of kappa, the limit exists and is non-trivial. So this limit is denoted by f naught, and we also call it the discrete transition behavior, or DTB for short. So this is what we mean. Yeah, this is the function that we want to reconstruct. And so so this blue curve now over here got the name. Right? We call it DTB. And of course, in practice, we never take the limit, so we just assume that epsilon is small enough so that this expression is close to the DTB, to the discrete transition behavior. Okay, so the goal is to compute this limit. Right. Okay, so let's see. The goal is to obtain an explicit expression for this limit. Okay, so let's discuss the setting. So R is the generalized Radon transform, which integrates over a family of capital N-dimensional smooth submanifolds. We call them SY. All SYs are inside an open set U, which sits inside Rn. So capital N can be any integer between 1 and little n minus 1. Okay, so we think about the set U as the image domain. It contains the support of our function f. So the submanifolds SY, these integration submanifolds are parameterized by points y. The points y range over an open set capital V, which is also in another copy of Rn. And we think about V as the data domain. And there is another object that we normally look at is the set, the manifolds Tx. These are inside V, right? So for each x, Tx is just a collection of side of all y, such that the corresponding Sy contains x. Okay, so okay. Now, a reconstruction from continuous data, so data G is just Rf, is obtained by this generic FBP formula. So G is the data, B is a fairly general pseudo-differential operator, and R star is a weighted adjoint of R. And so R star integrates over manifolds Tx. In what follows, G doesn't have to be the generalized Radon transform of any function f. But for simplicity in this talk, I will pretend that G is always Rf for some f. It just simplifies the presentation. Okay, and then associated with S is a smooth surface gamma in the data domain. The curve gamma, the surface gamma has the property that for any y on the gamma, the corresponding Sy is tangent to S somewhere. So all points on gamma has this property that then that you get this tangent surface. Okay. And so, first of all, we allow F to have a fairly general singularity across S. And B also is fairly general. So, possible choices, for instance, if B is such that the top symbol of R star BR is precisely 1, then the reconstruction is quasi-exact. So, F check minus F is smoother than F. Or if B is such that R star BR is pseudo-differential operator for the 0, then F check and F are in the same Sobolev space. And also, B could be such that the reconstruction is singularity enhancing. An example is lambda tomography, or it can even be singularity reducing. Okay, so this setting includes more general variety of transforms than was known before. So in particular, until recently, I could only deal with the case when capital N was little n minus 1, just codimension one Radon transforms. Now capital N can be anything. And in particular, it includes the most practically important case of the cone beam transform, where the ambient space is three-dimensional and we are integrating over one-dimensional lines or curves. Okay, so, and our main result is the derivation of an explicit formula for the DTB under these fairly general conditions. Also, we show that the DTB is actually just the convolution of the continuous transition behavior with a suitably scaled classical Radon transform of the interpolation curve. Okay, so what is the precise definition of the continuous transition behavior in the general case? It's actually pretty similar to the definition of the discrete transition behavior. So it's here on the first line. So we do the same trick as with the DTB. So we rescale the epsilon neighborhood around x naught, multiply the continuous reconstruction by epsilon to the kappa, take the limit as epsilon goes to 0. So for comparison, below, underneath here is written a formula for the DTB. So you see, the only difference is that in the top one, we have exact reconstruction, exact meaning with continuous data. And G epsilon means interpolated discrete data. Usually, CTB turned out to be a distribution homogeneous of degree negative kappa. Okay. There is another way to view this result. Operator R star can actually be viewed as a Fourier integral operator with a phase function, which is linear in the frequency variables. Right, so this is the phase function. So psi here is any vector valued function that satisfies some non-degeneracy conditions. And in the opposite, in the reverse direction, if we pick up psi, a non-degenerate psi like that, then it determines R and R star via these smooth manifolds Sy and Tx that have the same meaning as before. Right? And therefore, any Fourier integral operator f with a linear phase function like this can be represented in the form R star B for some pseudo-differential operator B, at least where R star is elliptic. It's very easy to see. We just take B to be R star inverse F, where R star inverse is an approximate right inverse of R star. Right. And then it's easy to see that B is actually a pseudo-differential operator, and modular regularizing operator F equals R star B. And therefore, the reconstruction algorithm can be viewed as an application of just some FIOF with a linear phase function to discrete data, regardless of any Radon transform. In the literature, various methods for applying FIOs to discrete data have been proposed. So, for instance, papers by Candace, Delaunay, and others. But it seems like the resolution of the reconstructed image, FG, for fairly general classes of FIOs F and distributions G has never been studied before. Analysis of such sort are important because generally FIO-based reconstruction is intended to recover the singularities of F. Reconstruction of the smooth part of F is usually not accurate, even if the data are ideal. For instance, even if we have continuous ideal data, reconstruction So most of the integral transforms don't have exact inversions. So at best, the reconstruction is quasi-exact. And our approach, which we call local resolution analysis, is well suited to the analysis of such problems because the analysis is localized to an immediate neighborhood of the singularities of it. Okay, so let's discuss the problem setup. Okay, so D is a data sampling matrix. Determinant D is 1, and we assume that discrete data G are given on the following lattice. And the reconstruction from discrete data is given by the same quote-unquote continuous inversion formula. We simply replace continuous data with its interpolated version GIPS. So initial set of assumptions, we assume that F is compactly supported. Its support is inside U, the data domain, image domain. So F is sufficiently smooth so that RF is a continuous function. So we can talk about pointwise values of RF. And the singular support of F, which we denote by S, is a smooth hypersurface. So pick some X naught and Xi naught in the normal bundle of S, and this pair is fixed throughout the talk. So our goal is to study F epsilon, the reconstruction in the neighborhood of X naught. So all the results are local. Therefore, we assume that U, the image domain, is some small neighborhood of X naught. And V, the data domain, is a small neighborhood of Y naught. So here, Y naught is such that the corresponding integration surface, S Y naught, is tangent to S precisely at X naught. So the singularity of F at X naught is reconstructed using data in a neighborhood of Y naught. So that's why you only need a small neighborhood around Y naught. Okay, this is how we describe parameterize these manifolds. So using a defining function, capital Phi, it has two parameters. So Y is the parameter that determines the manifold itself. And then T is the capital N-dimensional vector that parameterizes points on the manifold itself. And then we assume that when T equals 0 and Y equals Y naught, then Phi equals to X naught. Okay. Well, we introduce the following matrix M, which is actually the Jacobian matrix of the following two systems, two equations. Okay, the unknowns are T and Y. So the first equation says that the point X naught belongs to the surface S sub Y. And the second equation says that Xi naught is normal to SY at that point, at X naught. And of course, by assumption, we know that the pair T equals 0 and Y equals Y naught solves this system. We assume that the determinant of M is non-zero, which is a local Volcker condition. And so this condition guarantees that any singularity of F microlocally near X naught, Xi naught is visible from the data in the neighborhood of Y naught. Well, so these are the assumptions. So the first two assumptions mean that capital Phi is non-degenerate. Right? So the subscripts here denote the derivatives. So this means that SYs are smooth surfaces. Right? And this means that the derivatives, the matrix consisting of the derivatives of Phi with respect to T and Y has maximum rank N. And this is the Volcker condition that I mentioned. So all the derivatives here are evaluated at T equals 0 and Y equals Y naught. Okay, so what are the assumptions about the pseudo-differential operator beta and F? So beta, we assume that the principal symbol of beta is homogeneous of degree beta naught in the frequency variables, plus a lower degree pseudo-differential operator. So very non-restrictive assumption. And F is a conormal distribution associated with a smooth hypersurface S, such that its generalized Radon transform is given in this form. This is a fairly common expression. And so here, superscripts plus minus just denote two different functions. A plus and A minus are smooth, and subscript plus minus denote the kind of positive and negative part of a number. So P plus is same as P when P is positive, and 0 when P is negative, and similarly for P minus. Right? And so this is actually a very frequent occurrence when you have something like this. So for instance, in 2D, it's well known that the Radon transform has a similar type of singularity. It's a square root, one-sided square root type singularity. Okay, another assumption is that beta naught minus S naught minus N over 2 is not negative. And we also have another technical assumption, which I don't discuss. It's not very illuminating. Okay, so these are our assumptions. Then let's talk about the interpolation kernel. It's also important because we interpolate tomographic data using this kernel. So we have two assumptions. So phi is compactly supported, and all of its derivatives up to a certain order are bounded. And then it's exact up to a certain order. So exact meaning that if you substitute that it interpolates polynomials exactly up to a certain degree. Right? What are the degrees here? The degrees are determined by beta naught. Remember, beta naught is the order of beta of the pseudo-differential operator beta. If beta naught is not a natural number, then the ceiling of beta naught and the ceiling of this beta naught plus are the same. So phi is supposed to be exact up to the ceiling of beta naught, and it should have the same number of bounded derivatives. If beta naught is a natural number, then the ceiling of beta naught is the same as beta naught, but beta naught plus is just 1 plus beta. Okay. So you have finitely many derivatives, and you have finitely many exactness up to a finite order, up to a finite degree. Okay, and then this is the interpolate. This is what the interpolated data looks like. Pretty conventional. Okay. Okay, we need another key assumption. So before I describe it, well, I introduce this expression. So this is difference of matrices of second fundamental forms. So one second fundamental form is for the curve SY naught. Remember, it's a capital N-dimensional surface, right? But S itself is little n minus 1 dimensional. The two dimensions could be different. And therefore, we look at the subset. We look at the cross-section of capital S by a hyperplane that passes through X naught. And this plane contains Xi naught and the tangent space to S Y naught. And you get this S hat. Now S hat has the right dimension, and I can look at the difference of the second fundamental forms of these two surfaces. All right, so this is delta 2. And then this is a key definition. A pair X naught and Y naught is generic for the sampling matrix D if the following holds. So there is no integer vector M, which is non-zero, such that D inverse transpose M is normal to Tx naught at Y naught. Right? So for instance, if D is identity matrix, just think about a simple example. If D is an identity matrix, then there is no vector with integer components, which is normal, which is perpendicular to all tangent vectors to Tx naught at Y naught. And then the other condition is that the difference of the two forms is either positive definite or negative definite. Right, so the second condition is easy to understand. It's common. So basically, it just says that there is a good separation between S hat and Sy naught. Actually, this first condition is easy to understand too. So this is an illustration. So for instance, if this is Tx naught, and the grid here illustrates the sampling lattice. So the tangent space to Tx naught at Y naught is spanned by the vector 1, 0. So the vector 0, 1 is normal to it. 0, 1 has integer components, and therefore Y naught is degenerate. Is non-generic. It's a non-generic point. Here we have similar situation. The tangent vector to Tx naught is 1, minus 1. So the vector 1, 1 is perpendicular to it, and therefore this point is also non-generic. Right. So kind of yeah. So the angle should be kind of irrational number here. Well, not the angle, but the tangent. Okay. And this is the main result. So suppose kappa is positive. Okay. Then on the left, we have this limit that gives the discrete transition behavior. And so it turns out the discrete transition behavior is given by this convolution. You take the continuous transition behavior and convolve it with the classical Radon transform of the interpolation kernel. And this classical Radon transform is scaled by the factor C, which is explicitly computed as well. I'll talk about it on the next slide. All right, so this is, okay, again, so as a reminder, so this is the setup. This is the point X naught. This is the point Y naught from which the singularity of F is visible. So Xi naught is normal to X naught here. Theta naught is normal to gamma here. And so, okay. Yes, and X check is this dilated variable. Okay. So let's discuss a little bit more about the what CTB is, the continuous transition behavior. It's a homogeneous distribution, which is the leading singular term of the continuous reconstruction F check. Right? So it's given by this limit. It's given by this limit. So again, so the limit uses the same idea. You dilate the variable here by factor 1 over epsilon, and then multiply by epsilon to the kappa. And then computation of the continuous transition behavior is fairly standard. You can either do it using the stationary phase method or using well-known calculus of free integral operators. So F is a conormal distribution. It has certain principal symbol. Then you can apply R to it, B and R star. So one way or the other, this is a fairly standard calculation to come up with the CTB. Okay, so what is this scaling factor C that affects the resolution? Okay, so for Y naught, we have this surface Sy naught that passes through X naught. And then let's shift a point along this direction theta naught by the directed distance delta. So you'll get a point Y prime. That could be positive or negative. Then the corresponding surface Sy will shift it will become Sy prime. And to first order, it will shift by amount of delta prime along this direction xi naught. So delta prime is a directed distance along xi naught. And then C is just the ratio of delta prime over delta in the limit as delta goes to 0. And of course, this limit can be computed explicitly if the Radon transform is known. And then a corollary to our result is that the resolution is basically epsilon times epsilon value of C. Okay, and so that's the resolution. And okay, so let's to recap, basically the result says that the discrete transition, so what you get from discrete data is what you get from continuous data convolved with a certain kernel, which is a rescaled version of the classical Radon transform. So this kernel is completely independent of the reconstruction operator beta, of what happens with F. It depends only on data sampling, on the geometry of the Radon transform, and on the kernel phi. That's it. So it's a fundamental object. And so this relationship applies in a generic case regardless of what beta and F is. Okay, so and now since you have this discrete transition behavior, since you have this curve, then any measure of resolution can be accurately computed. So to illustrate by a simple example, this is in 2D. A phantom was just a disk, and I took a point on the boundary of the disk. This is the ideal profile, right? And I performed exact reconstruction. And then one magenta curve is actually the reconstructed curve. And the predicted curve, according to this formula on top, is green. And you see the match is good. Okay, so we derive the formula for the, to summarize, we derive the formula for the resolution of reconstruction from discrete data. And the formula is easy to use, can be applied to at any point along any direction. And it applies to a wide range of tomographies. It could be conventional X-ray, Compton, thermoacoustic, and others. It has certain numerous applications, including the most practically important cone beam CT. And it also gives a formula for the resolution of reconstruction when reconstruction is performed by any FIO with a linear phase function. Okay, thank you very much.